Assalamu alaikum and welcome to the second tutorial of the semester, which is traditionally a little before the final exams. So it is not only a solution of the quizzes in the midterm, but also helps you in preparing for the finals. We will start with the midterm exam. Question 1 and 2, as always, are the multiple choice and the true false. So let's start with a few examples of the multiple choice. Mode 1 testing for plane strain fracture toughness refers to which mode of a specimen and load orientation? Opening or tensile, sliding, tearing, any of these. So if you know, it is opening or tensile mode. Fracture toughness of steels is generally dash that for aluminum alloys, higher than, same as, lower than, any of the above. So if you remember even a little about materials, then you would know that fracture toughness of steels is generally quite high compared to aluminum alloys, so it is higher than. Dash of test specimen must be large to meet the condition of plane strain, thickness, length, strength, ductility. So if you remember, there was even a formula, capital B is equal to something, that is the thickness of the test specimen, because if the thickness is large, then the strain in the third direction is negligible and the specimen becomes plane strain. Dash failure can occur even when applied loads are in the elastic region. Fatigue and wear, tensile. So you know that the answer is fatigue and wear. Fatigue loads, of course, I mean, you are even half the yield strength, but the load is cyclic, it keeps on repeating, the material can fail. And wear has got nothing to do with what is the amount of the load. Wear is the surface erosion, right? So fatigue and wear can happen even when the loads are in the elastic region. When uniaxial tensile load is applied perpendicular to the crack surface, loading type is called mode 1, opening mode, tensile mode, all three. So you know that all three names are correct. When the direction of the force applied is roughly perpendicular to the direction of the crack opening, then it is mode 1 or opening mode or tensile mode. So the correct answer is all three. Let's go to the second part of these two questions, which is the true false type. Applied load is tangential to the crack surface in mode 1 loading. What is your answer? Yes, you are right. It is false, right? Because mode 1 load is perpendicular, not tangential. Variation of stress distribution with distance from a sharp crack is linear in nature. What is your answer? False. You have several diagrams that there is the crack tip, and we draw the profile of the stress variation as you go away from the crack tip, and it is always a non-linear curve, not linear. Value of a stress concentration factor decreases with increasing fillet radius for a 90-degree profile change. Yes or not? Right. So yes, you are right. It is true, because if the fillet radius is very large, right, then the stress concentration factor is large. Critical stress for failure varies linearly with a specific surface energy. What is your response? True, right? But so remember, it is the relationship between critical stress and a specific surface energy. So with these two are, yes, almost linear in nature, not the other factors. A stress concentration factor Kt is also known as the stress intensity factor K1. What is your response? Yes. If you said false, you are right, because stress concentration you studied in solid mechanics and machine design, but in stress intensity you also talk of the geometry part and so on, of the crack type and so forth, which was not there in KT. So this was a few examples from a multiple choice and true false. Let's move to the main questions now, the numerical problems. Question 3. This is the question. Relationship for minimum creep rate as a function of a stress and temperature is given below, right? It is given here. A steady state creep rate data are given in the following table. For nickel at 1000 Celsius, so this table contains the values. If it is known that the activation energy for creep is 210,000 joules per mole, determine the steady state creep rate at a temperature of 900 Celsius and a stress of 20 megapascal. Value of the universal gas constant is 8.314 per mole per Kelvin. Right, so this is like, this problem belongs to a certain chapter because we are talking about activation energy and so on. But if the equation is given here inside the problem, then this could be asked anytime, right? So here you see, a steady state strain rate, right, per second, 10 raised to minus 7 when the applied stress is 15 megapascal, 10 raised to minus 6 when the applied stress is 4.5 megapascal. So these are given, the equation is given, right? So put the values there, that 10 raised to minus 4 strain rate, 10 raised to minus 4 is equal to C unknown, sigma raised to n, sigma is 15 megapascal, n is unknown, exponent of minus QC by RT. QC is the activation energy, 210,000 joule per mole. For QC, write this value. R 8.314 per mole per Kelvin. Temperature, right? Temperature is 1000 Celsius. So this is one equation. Secondly, 10 raised to minus 6, same equation. This is the strain rate. C sigma raised to n, sigma this time is 4.5 megapascal. Exponent Q, R, T, those values are the same. So you write this equation twice, right? And then you solve them together and you will find the unknowns C and N, right? This is C and N. Once you find them, then in the final condition that the temperature is now 900, the stress is 20 megapascal, then find the strain rate. So this is a very, it may take a few minutes, step by step, but there is almost nothing to it in terms of difficulty level, right? So I am just writing that this is your equation, right? So 10 raised to minus 4 was the strain rate per second for 15 megapascal. The rest of the values are the same. So we have just simplified that. We will say the C is on one side. Then 10 raised to minus 6 is at a stress of 4.5 megapascal. So this is equation 1, this is equation 2. Divide one equation by the other, C and C will cancel out, only N will be there. Once N is there, then you can take, this is exponent, take ln, right? Take ln or log, and the exponent will come down. So you solve the two together, you get N is equal to, say, roughly 3.82, C is roughly 1.33. Once you get them, then put them here again, that now the value of C is known, the value of N is known, and sigma this time is 20 megapascal, and temperature this time was given to you, so 273 plus that. So now you find the actual value, 5.52 into 10 raised to minus 5 per second. The units, remember, right? Every time I grade your quizzes and your midterms and so on, I repeat so many times in the classroom that only a numerical value has no meaning. If it is miles or kilometers or meters or millimeters, right? They are all different values, even if the number is the same. So I am very particular about your answers coming with the proper correct units. So this is a strain rate, right? A strain is no unit, a strain rate is no unit per second, right? Per unit time. So this was the question. As I just said, a step 1, one equation, a step 2, second equation, solve them together, find the two constants, a step 3, solve the total question. Let's go to the next question now. A particular chemical processing plant consists of a number of similar reactors which operate at temperatures ranging from -70 to 350 Celsius. It is desired to use a single alloy to manufacture all the reactor vessels over a range of temperature -100 to +400. Fracture toughness of this alloy is K1C is equal to 63 plus T by 10 megapascal root meter. Variation of yield strength with temperature is shown below, right? So there are two things, that because you are varying from -100 to 400, then the values of fracture toughness you can find from here. Every time -100 Celsius, put the T there, 400, right? So these values of K1C are there at different temperatures, and the values of yield strength at -100, 0, 100, 200, 300, 400. So yield strength is directly given in megapascal units, and K1C you can find at the same, at -100, 0, 100, find the values of K1C. The vessels have a wall thickness of 15 millimeter and are to be designed on the basis of leak before break. Based on material performance rather than operating conditions, graphically determine the temperature at which yield becomes more likely than fracture. That is, the design criterion changes from fracture to yield control. Any comments? So we don't want to solve it by equations. The values of fracture toughness K1C at different temperatures is calculated by you. The values of the yield strength at different temperatures is given, right? You have a yield leak before break type of criterion. So now you think a little. As I keep on telling you that the best way to use these tutorials or the class examples or anything where we actually solve it for you, but the best way for you to prepare is that at this point of the video, pause the video. Don't go further. This is the question. You have done it in the midterm, but do it again as a fresh problem so that your understanding becomes very strong. And don't give up. Don't give up that I will quickly look at the solution, because once you do that, you become weak. You don't, challenge yourself. And if a slightly more difficult question comes up on the exam or something, then you don't have the solution. So stop here, solve it again on a rough paper. Once you are 100% sure that you are right, then go ahead and look at the solution.